This is Dr. B and an introduction to the electron. To study the electron, it helps to have some knowledge about light. The reason is, to cut to the chase, that the electron is so small that it behaves similar to light in some ways. It, for example, has wave-like properties, which light does. How do we know that light does that? If you take a flashlight or a beam of light and you run it through a wall that has a couple of slits, it can be demonstrated that you can see more than 2 lines of light on the background here. You can see 4 or perhaps 8 under the right conditions, which is only possible if light travels in waves. And in fact, it's the exact same thing that you can see with water, for example, if it goes through some rocks, for example, with a couple of slits right here. You can get interference leading to multiple wave patterns. The same thing is true as light, so light travels in waves. The waves must have a length, they must have a frequency with which they pass a given point, and they must have a speed, right? The higher the frequency, the shorter the wavelength, right? Because they'll be more frequent, right? So the speed of light is equal to wavelength times frequency. The speed of light is given as 3 times 10 to the 8th meters per second. That's 300 million meters every second. That is really, really fast. And frequency is a little hard for students to understand, but it's just how often it goes by a fixed point. How frequent is that wave? And therefore, it means per second. 8 times per second, 17 times per minute, whatever it might be. And per means draw a line, 1 over it. Therefore, frequency is seconds to the minus 1. Since that's an awkward term, it sometimes is referred to simply as a hertz, but that's what frequency is, how often. And the wavelength is just in meters. Here's a higher frequency than this, for example. Lambda is the symbol normally given for wavelength. We're just going to call it W. And if you have a short wavelength like here, it's more frequent, so it has a higher frequency since these are going at the same speed. High frequency for light means that it's potentially dangerous. You're going from, visible to ultraviolet to gamma rays, things like that. They become more frequent. They hit the surface more often, more dangerous. If it's a long wavelength, like radio waves, cell phone waves, right, they are lower frequency, much, much lower. They can be hundreds of meters in terms of their wavelength, and they're considered to be harmless, which is good to know. And let's do a calculation. If you'd like to do this completely, now's a good time to take out your calculator. What's the wavelength of violet light? We know that its frequency is 7.23 times 10 to the 14th seconds to the minus 1, that's hertz. So if they want wavelength, I think we're going to have to rearrange. So wavelength equals the speed of light over frequency. I don't like nanometers because if the speed of light is in meters per second, we better change that to nanometers. And nano means 10 to the minus 9th. We can do that. So let's solve it first for meters, then change it to nanometers. Rearrange. Plug in our numbers. We know that the speed of light is 3 times 10 to the 8th meters per second, and the frequency is given in inverse seconds, which is nice, so we end up with meters. And if you just multiply that times 10 to the minus 9th meters is a nanometer, you can also do a nanometer is a meter is 10 to the 9th nanometers. Either way, you find that you have 415 nanometers is the wavelength of violet light. This is an introduction to the electron.